Now I get to F. 0 at F. Is it 0 anywhere else? And I don't know if I stated this verbally, I'm working under the assumption that everyone's read the problem already. It stops at K, by the way.
So the velocity will be 0 at K as well.
Yep, there we go. Now, just because you hit 0 doesn't mean it's necessarily going to flip from positive to negative, but in this case it does. Between F and K, it's traveling to the left, which is the negative direction. So the shading for velocity would be positive, and then 0, and then negative, and then 0.
Would it also be negative because there's friction when you're going that way, so it's slowing down?
Slowing down would affect acceleration.
So would A be included? Sorry, I'm doing the chart method. Would A be included in the positive?
Yes, because the problem, in the problem it states it's already moving to the right at the beginning of the problem.
Okay.
Some problems it starts at rest, some problems it's already moving, as in this case.
And E is included too, in the positive?
Yes, so what's happening at E and F, and this has confused some students, it's that idea that once something touches, it doesn't stop instantaneously. Similar to the problem with, we dropped the vase, and when it hit the pavement, it does not stop instantaneously. It does take some amount of time, a small amount of time, but it does take some time to change. So in this particular case, net, ball, or wall and ball, as in some problems, is cruising along, cruising along, cruising along. E is that first point where it touches the wall. So that would be E. There's some flexing going on here as the ball squishes. F, and then it bounces back. G is that last moment where it's touching the wall, and then starts traveling. So at E, the ball is still officially moving to the right. It's not going to move far, but it is still moving to the right.
So with the negative side, F would not be included, and it would be F through K not included, right?
So F through K not included?
F and then K are not included in the negative.
Oh, that is correct.
Okay.
So up here, the velocity, the positive includes A through F not included, and then we have F and K, and then FK with parentheses to indicate we're not including them in the negative, which is what Bailey just said. And then the hard one, or the one that gives most students issues. It depends on how quickly you can break yourself of the idea that of what acceleration means. In order for there to be acceleration, there must be some net force acting on an object. Or think of it this way: the velocity changes means that there's acceleration. When is there an additional force acting on the puck? This puck is cruising along, hits the net, and bounces back. When is there something else acting on the puck? Yep, that's when there's a hockey stick that hits it. When else is there something else acting on the puck?
F.
When it hits F, when it hits F,
Okay, and F definitely.
and the friction, and E and G.
All the way from E to F, it's touching the net, and then from G onward, or G to I, there's friction. So those are the things that are gonna mess with it. And, let's see. I do need to change one thing here, though. Oh. Friction's acting all the way to K. sorry, not I. That messed up because the original problem, I had fewer letters and I was the end. Friction's acting all the way to the end. All right, so from B to C, the puck's moving this way. The stick hits it towards the net. Is it going to speed up or slow down?
Speed up.
So therefore, acceleration and velocity have the same sign. Or, thinking of it this way, is that there's this net force acting on the puck in the positive direction. So between B and C, my acceleration is positive. What about from between A and B? Is the puck speeding up or slowing down?
No,
Pardon?
it's not doing either.
Okay, what's the acceleration?
0.
Including at A and at B. So, what happens when I don't have vertical lines? That's positive. Then, once it hits point C, the hockey stick's not touching anymore. It's just clear sailing till it gets to the net. So, there's nothing to change it. So C, D, D, E, and then E, it touches the net. Which way is the net force going to act on the puck once it touches the net?
Negative direction.
Yeah, the net is pushing back on it. It's going to cause it to slow down and then speed up. But the force is in the negative direction. Puts us to there.
Wouldn't it be positive at G?
It would not be, let's see, the original problem. Yeah, this is one of those problems where there's a mistake. Why don't I take this one?
Because the direction is changed at G.
Yeah, it does change. G is the last moment it's touching the net, pushing it that way. I also have it the first moment it's touching friction, so we've got a mess there. I've gotten better at doing these problems so that doesn't pop up. I think that was the only time it really was that bad. G, we got something funky going on. Once it gets to the friction, so it's now traveling to the left, friction's acting on it. Which way is friction acting on it?
The opposite way.
To the right, isn't it?
So therefore, it's positive. And then we have this, what's happening at K? It stops moving, but is there acceleration?
Yeah, because the friction stops, right? Or is it continuing with the friction?
I mean, the friction's gonna act on it as long as it wants to move or is moving, as long as there's desired relative motion. Once the puck stops, it doesn't want to move anymore, assuming it's level ice. So afterwards, it's definitely 0. But at the moment of K, I would contend that there is still acceleration going on. And the reason for that is that if you're at a traffic light and the light changes green, you put your foot on the gas and you take off. There is a moment there in which you have not moved yet, but your velocity does change, and therefore there is acceleration. If acceleration has to be 0 when you're not moving, then you would never move at all. So there has to be a moment. And since this is the moment that it stops, that is the moment that, it's that last moment that we actually still have friction acting on it, the last moment that there is a change in velocity. And then that moment just after K, there is no more acceleration.
I still don't understand why the acceleration is positive between G and K.
So we can look at it two different ways. One way, think about it in terms of forces. As it's sliding this way, I have weight acting down, I have normal force acting up, and I have friction opposing the motion. These two will balance each other out, because it's not coming off the ice or into the ice. So my net force is friction, which is to the right, positive.
Okay.
Other way of looking at it, while it's going from G to K, it is slowing down. If an object is slowing down, velocity and acceleration are opposites. While it's slowing down, my velocity is negative, therefore, that's positive.
Okay.
That second way of thinking about it is a lot more difficult to apply when you're dealing with an object that has stopped for a moment or changed direction. Another way of looking at the exact same thing, let's say that we're going negative 20 meters per second at this point and going 0 meters per second at this point. What is my change in velocity?
20 meters per second. 20 meters per second.
Yes, positive. Because the acceleration will have the same sign as change in velocity.
Yeah, thank you.
Right? A test level problem that had some issues, so apologies again, but hopefully you understand at least the gist of how to approach it. And also an example here of going from, when you hit 0, you're not necessarily going to change signs immediately after that, because we have several zeros in a row here. Zeros and pop up to positive and zeros again. And then there's that mess that happens at GM. The other issue was that I forgot to put an extra letter. There's a letter that should have been in here that wasn't. I overcompensated. All right, any other questions before we talk about the lab? All right. We've done the graphing lab, and then we did equilibrium lab. So you have dealt with the lab questions. This time you'll be using a motion detector. Grab more in a minute. The motion detector boxes should come with a motion detector, and it should come with a cable like that. This part of the motion detector can flip up if that is convenient for you. I think a good part of it, I have it so that the screen is facing upwards like that, and you can just put this right on the ground. I talk about moving something in front of it. You can move the LabQuest box if you want, you can move a book, things like that. Some things to be careful of, say I'm using this box in front of the motion detector. Anything within about 18 centimeters of the detector, 17, 18, somewhere in there, anything within that range, it cannot tell that it's there. Or, change that, it can tell it's there, but it won't differentiate between 5 centimeters and 10 centimeters and 15 centimeters. It's based on the wavelength of the sound that's being used. It's an improvement over the 50 centimeters that the older ones had. So when you're moving it in front, don't start it down here, start it something like that. Grab a ruler if you want to be more precise. Another issue sometimes students do is that when they move it, they'll do something like this. So it's over the beam, and then suddenly it's not over the beam. And so what the beam's gonna do is it's gonna go, oh, ceiling. Well, or, ooh, this thing has suddenly jumped several meters up into the air. So when you move it, sort of a full body thing, or do squats, whatever you need to do, but you're moving it in front of it like that. As you're moving it, if you want a smooth curve, so let's say I took an object and I just drop it right over the sensor, And if you're gonna do that, please make sure it's not something that's gonna hurt it. What you would see is it starts out far away, so if I did position, it would actually say position and time. It would look something like that. Or if you reversed it and suddenly you move up with a constant acceleration, it would look like that. If you're moving in front of it and suddenly it's not in the beam anymore, what you might see is a spike like that. That tells you that suddenly the thing was not in the beam. The beam is sound, it's bouncing sound off it, it's in essence a sonar. Now, if this is position time, I think you can pretty much tell, oh, it could go like that. But if you look at the velocity time graph, so the way you do that, you click on that and you'll suddenly be given a choice of things to pick, and you pick velocity. The more bumps you have in this graph, the worse it's gonna be for velocity. Because what the machine sees is that it's, let's say 50 centimeters away, and then suddenly 3 meters away like that. That means it had to travel incredibly fast. And then acceleration is gonna be even worse. So the bumpier this is, the worse velocity will be, and acceleration is absolutely horrendous. So try to be as smooth as possible. Now, we're not doing precise measurements in this lab, so it's less crucial than some other labs that we have done, or I have done in previous classes. In the last part, or next to last part, when you're doing the kinesiology bit, when you're actually doing movement in front of it, I mean, you can do movement up and down like that, or set it like this and move it like that. In the original version of the lab, people were walking it off. They were walking in front of it. It works really well if you can move smoothly, but people had difficulty walking like the gentleman in that episode of Buffy the Vampire Slayer. So, if you're moving something in front of it, recognize if your hand is shaking, it will show up. So just move it as smoothly as you can and just do the best. However, when it actually comes to doing plots, if I have an object, move it away from the origin at a steadily increasing velocity or speed. Ideally, it looks like this. The velocity looks like that. The acceleration looks like that. The reality is, this one is probably going to look like that. This one is going to look like that. And this one is going to look like that. So there's a certain amount of understanding what's really going on here and knowing what it's supposed to look like. And by that, it is actually possible to do this lab without being in here with the equipment. The reason why I don't just send you off with it and say, hey, do this and come back with it, is that some students need to actually physically see, hey, I'm moving like this is the way it shows up as position, velocity, and acceleration. So, with that being said, four groups of 3. And I will be handing the second lab back, the linear motion lab. If you don't understand why certain things were taken off, please ask. And I will get the face shields because you'll be near each other. And remember to, as always, rejoice, because this is physics. All right, so face shields, motion sensors, lap rests. Oh, and if somebody could stop the recording.
It is.
I just like Riddle. It's
That's not going.
no, it is going.
And hopefully